Hi class, this is the lecture video for chapter 3, which is functions, okay? There's quite a bit to cover in this chapter, and functions, okay, is this interesting idea. Is a function is a rule that matches each number in your variable x with another number in your variable y, okay? And exactly every x will have one y to match it. And it's a little bit different than an equation because in the past, an equation would be variables equaling a number specifically. But a function is when you have essentially a list of x's, possible values for x's, which we call domain, that match to an exactly a specific value for y, which we call range, okay? So in a function, one thing to note is that there is only one y value for each value of x. And here, instead of y, we often use f. Oh, I don't like that color. Give me a second. Okay, we often use f of x to denote y. This is just tells you that this is a function of x. Okay, and now f is not special. In the future, or actually even today, you'll see many other denotions. You can have, g of x or h of x, and it doesn't have to be x either, right? For example, later in economics, you'll learn utility functions, which is u of something, let's say usually consumption, right? So it can be u of we don't use c because c is usually for cost, but say u of I, then that means it's a function of this variable I. So it doesn't matter, these letters are not super special, just this form is what tells you this function is, okay? So now I hope this makes sense, okay? If not, well, go back and read some more and write down your questions and do some practices, and then ask me in class on Thursday, okay? Let's just do some quick examples, okay, to evaluate some functions, right? So let's say we have a function that says, let's get rid of the lines for now, since we're not drawing any graphs. So we say we have f of x equals x cubed minus 2x squared plus 3x plus 100. So again, this is a function because it tells you this rule of how x and y, which is denoted by f of x, match each other, right? So for example, you can say, okay, well, in this case, what is f of 2? Then you say, well, this is 2 cubed minus 2 times 2 squared plus 3 times 2 plus 100. And that will give you, okay, 8 minus 8 plus 6 plus 100, and which will be 106. Okay, and similarly, if you don't have a specific value of x, you can say, well, what is f of a? A is any real number, any constant. Well, in that case, then this tells you f of a equals a cubed plus 2, whoops, not plus, minus 2 times a squared plus 3a plus 100, right? And here again, a is a real number, okay? And so any real number, you just plug it in, right? Similarly then, you can say, well, x in this case can be a little function of its own, right? So f, what if it's f of a plus 1, right? X equals a plus 1. Well, then same thing. You just do a plus 1 cubed minus 2 times a minus 1 plus 3 times a minus 1, or sorry, not minus, plus 1, okay, and plus 100. And then you can, well, actually, I'm not going to expand this out because there's a cube term. It's going to be, you know, a little bit of a calculation, but you know, the bottom line is the principle here is that whatever you put in the parentheses right here by your function form, then you just plug that entire parentheses in as the x, and then that would give you the way to solve the function. Okay, and now what if you have f of a plus 1 like this? What do? Well, then that would just simply be a cubed minus 2a squared plus 3a plus 100. That's your f, then plus 1. Okay, so at the end, instead of 100, you'll get 101. So make sure the parentheses right here by the f really controls what goes into the equation and how that term goes into the equation. So if something is in the parentheses, then you plug in that whole thing into the place of x for the entire equation. If something is outside of the parentheses there, then you just add it on at the very end of the whole equation. Okay. All right. So now we can do a little bit more than just one function, right? So you can have, let's say, another function. Okay, again, the letter doesn't matter, so you can have a big f of x, and that still means a function of x. Okay, it can be u, it can be t, it can be, you know, whatever letter you want to use. It just tells you it's a function of whatever is in the parentheses. And let's say here, f of x is x squared minus 8x, right? Say that is the function. And then what if I want you to find what is f of 5 minus f of 2? What do? Well, you just plug in 5 into the functional form and then plug 2 into the functional form and then subtract each other, right? So this equals 5 squared minus 8 times 5 minus 2 squared minus 8 times 2, okay? And so if you want to calculate this out, this equals 25 minus 40 minus 4 minus 16, and that gives you a negative 15 minus negative 12, which is plus 12, so that gives you negative 3, okay? And so you can play with the different things you can plug in, right? So similarly, what if you have f of, x plus h? Well, then this would equal x plus h squared minus 8 times x plus h. Again, then you can expand x plus h squared and then combine the terms into the new functional form that it would take. Okay. Now you might say, okay, well, that kind of makes sense, right? So what's the big deal with all these different things? Well, the big deal is that we can use your functional form, or your functions, I should say, to solve a lot of mathematical problems. Now, this chapter's job is to just introduce a whole bunch of different functions. So we don't have a whole lot of examples that relate to economics yet, but as we go on, then this becomes the basis of the rest of the semester, right? Because with different kind of functions, then you can then solve for different types of scenarios. Okay, so another type of function that you can use is something called piecewise function. Okay, piecewise function means that this function will have different intervals in the function, and it depends on which interval you are in, the functional form will be different. Okay, for example, let's say that you get into real estate and you become a real estate broker, and you charge a commission, so your commission, oops, okay, is 6% for any sale up to $300,000. Okay, so I should say up to, okay, $300,000. And then, okay, for any sale more than 300,000, your commission becomes $6,000, okay, plus 4%. Now, then if I were to ask you, well, what is the function for your commission structure, then you would say, okay, my function for my commission is f of x equals, okay, 6%, which is 0.06 times x. X here is the value of the sale. F of x is your commission, right? So this is commission right here, okay? Your x is the value of sale. So, but this is true when x is less than or equal to 300,000, okay? And if it is above 300,000, then this becomes 6,000 plus 0.04x, where when x is greater than 300,000, okay? And then where here x is the sale value of a home. Okay, so this is a functional form. It's called a piecewise function, where the function takes on different form, depends on where you are in the domain. Remember, we said the domain is the value your x can take on. So you can break the domain into different intervals, and in each interval, depends on which interval you are, your functional form can be different. Okay, but nonetheless, okay, this is a function of what you're looking at, right? So now then, if this is the case, I can then figure out, okay, what is, the value of a $200,000 home being sold? Then you can say, oh, $200,000, that falls in this functional form. So that equals 0.06 times 200,000, okay, which gives you, okay, $12,000. Okay, so that's how you solve that. But you can say, well, similarly, what is a home of $500,000? Then that will be 6,000 plus, okay, 0.04 times 500,000. Okay, and that gives you 6,000 plus 20,000, and that is $26,000. Okay, so, and because with the 500,000, it falls in this range, so it takes on the second functional form in your piecewise function. Okay, all right. Now again, okay, I hope when I give you an example and explain the scenario, you pause the video, try to solve it yourself, and then watch my solution so that you can do the practice instead of just following along and thinking, oh yeah, that makes sense, right? This is math, and if you follow me, it will make sense, but that does not mean you can somehow do it yourself, right? Because math is very logical. Okay, all right, now, let's look at specifically how to find the domains of some functions, right? So let's say you have a function where it's fx equals 1 over x minus 2, and I want you to find the domain for this function. Again, the domain is the values that x can take on, and the values your y or fx can take on is called the range. Right, so the domain here, you can see, well, clearly, okay, this function would be undefined if the denominator is 0. So you know that the only restriction I have is x minus 2 cannot be 0. So that means your x cannot be 2. So the domain then is negative infinity all the way up to 2, combining 2 to Oh, that's a terrible. Okay, 2 to infinity. So essentially, it's anything other than 2, x can take the form of, right? So that's how to do one. Another example is h of x, again, letters don't matter, is the square root of x minus 2. Okay, now here, your domain and your range can only be real numbers. They cannot be imaginary. So as a result, you know x minus 2 has to be greater than or equal to 0, right? So the domain then becomes x is greater than or equal to 2. Because if it's a negative number in your square root, then you get into the imaginary numbers and it's not real numbers anymore. So and that can be solutions for certain things, but for the purpose of this class, we will see occasional examples like that, but 99% of the time you're dealing with real numbers, right? Because economics is complicated enough with modeling and mathematics, and if we get into the imaginary numbers, then I think a lot of people will be lost. Right? All right. Now, there is a vertical line test to see if if you see an equation, or I should say, if you see a graph, whether that represents a function. Remember, we said that for every x, there can only be one value of y, right? So that means for whatever graph you see, okay, if you do a vertical line test, vertical line test, okay, and then you can see if this graph represents a function or not, okay? So the way to do this test is if you draw a vertical line and it intersects at more than one point, then that graph does not represent a function, okay? For example, if you have your graph like this, and then you have this is your plane, and then if you have a graph that does something like this, okay, you can draw any vertical line. You can see that each vertical line only intersects with this graph you have drawn at one point. This tells you it is indeed representing a function. But similarly, if you have a graph that looks something like this all the way through, and you draw a vertical line, you can see it intersects with this particular graph at multiple points, then that means the squiggly line that you have just drawn does not represent a function, okay? All right, okay. Now, so this is all still introductory stuff. This is a quite long chapter, so let's do a couple more examples and then move on, right? So let's say if I have a function that says f of x equals 6 divided by the square root of 7x plus 10, then I ask you, what is the domain? What do you do? Well, first of all, we know that 7x plus 10 cannot be negative, right? So we know that 7x plus 10 has to be greater than or equal to 0. But we also know that the denominator cannot be 0. So the square root of 7x plus 10 cannot be 0. Well, so if we call this condition 1, this condition 2, then condition 2 would tell you then 7x plus 10 cannot be 0, right? Because the only time your square root equals 0 is because what's inside of the square root is 0. So, well, in that case, then combining these two, 1 and 2 together really is saying, okay, so 1 and 2 together is really saying then 7x plus 10 has to be greater than 0. And that gives you x is greater than negative 7 divided by 10. Okay, so just keep that in mind when you're looking at a function. You have to think what kind of values that x can take on in order to find what kind of solutions this function can give you. And sometimes you might look at this and just conclude one is what you need. You know, this inequality here is what you need for the value of x, but you have to be careful, right? And remember, in this particular case, for example, there are two conditions you need to consider. Okay. All right. Okay, so let's see. Next, what I want to talk about is whether, let's see, we have different kind of functional forms we can use, right? So let's look at a supply and demand example. Okay, so let's say that you have the supply and demand function as follows. So supply is 9x plus 8. Okay, demand is 148 minus 5x. Okay, and then I ask you, well, what is your equilibrium point? Okay, so what is your equilibrium point? Well, you should know, hopefully, that at equilibrium, okay, the definition tells you that is when your quantity supplied equals quantity demanded, and that's the only point when that is true. So you know at equilibrium, your S of x should equal d of x, right? Your quantity supplied and quantity demanded should equal each other. So then you can do, okay, well then that's 9x plus 8 equals 148 minus 5x. So I move negative 5x to the left-hand side of the equation and make it into a positive. So that's 14x. Then you can move the 8 to the right-hand side and make it a negative term. So 148 minus 8 is 140. Divide both sides by 14. And that gives you x at, equilibrium. We usually put a star. That is, okay, 10. Okay. So now remember, in your supply and demand world, okay, x on the horizontal axis, that is quantity. So here, quantity is 10. Then how do I find what your price is? Well, the price, you just plug x back into either the supply and demand function, and you get, if you use the S of 10, the supply function, this is 9 times 10 plus 8, which gives you 98. So that means your price, or your price is going to be at $98, right? So your equilibrium point is then, okay, 10 for the quantity and 98 for the price. Okay, all right, hope that makes sense. Okay, and let's look at another quick example of supply and demand. All right, so let's look at another example. Okay, let's say that for the piano guys, I don't know if you guys like them, but they're one of my favorite musical groups. And let's say they have we know they have just released a new album, and I considered buying their CDs, but then I was like, well, I'll just listen to them online at Amazon Music or something. But they did sell a lot of CDs, right? So let's say that they looked at their cost and determined that the cost of producing their CDs, okay, is 14 cents per CD, okay, plus say $2,000, 780.4, okay, per month in fixed cost, because they have to have equipment and etc. So they had to put that much down before the CDs can be produced. Okay, and then let's say the CDs, the price of your CDs is $20 each. Okay, I can't remember exactly how much they charge. I think might be a little bit less than this, but this is the condition, okay, for the example here for the piano guys. Now my question is, well, first of all, okay, what is the revenue function, right? So the revenue function is, let's call it Rx. Okay, again, the letter doesn't matter. R here just to help you remember we're talking about revenue. Well, revenue we know is price times quantity, right? Here X is your quantity. So how many, and price is $20. So how many dollars can you bring in when you sell X CDs? Well, that's 20 times X, right? So if you sell one CD, that's $20 in revenue. If you sell 1,000 CDs, that's $20,000 in revenue. Okay, I hope that makes sense. Now, next question is, well, what is the cost function, okay, for their production? Now, the cost production, again, is you can denote it with a C, okay? So C of X tells you how many CDs they have produced and how much cost that is. And this equals 0.14 times X, right? 14 cents per CD times however many CDs plus the fixed cost, which is 2,780.4 per month, okay? Now I can ask you, well, then what is the profit function, okay? Hopefully you remember profit function, okay? Which the profit we use in economics is pi. So pi of X, that equals your revenue minus your cost, right? So that is your 20X, your revenue, minus your cost, which is 0.14X, whoops, plus 2780.4, and that gives you the revenue. I mean, sorry, the profit. So this then becomes 19.86x minus 278.0.4. Okay, so that's your profit revenue. Now, once we talk about derivatives, we can figure out what is the quantity that will maximize their profit, how many CDs they should sell to maximize their profit. But we're not quite there yet. So the best we can do right now is to ask the question, well, where is their break-even point, right? How many CDs do they have to sell, okay, in order to break even, in order to make sure they no longer are at a loss? Well, that is when to break even means your profit has to equal 0, right? So that means 19.86x minus 2780.4 equals 0. And then if you solve that, that gives you x is 140. So they need to sell 140 CDs in order to break even. Okay. Now, anyway, so I hope this makes sense and help you kind of see a little bit of the relevance in economics. Okay. Before we can move on to something else. Okay. All right, let's look at, let's look at a similar example, but maybe a little bit complicated, right? So let's say that you own a bicycle store, or actually I should say you own a bicycle tire store, okay? And you're making and selling tires, and you notice that when your price of tires, okay, when price is $1.45, okay, you can sell 29 tires. But if you drop your price to $1.15, you can sell 41 tires. So just do a win here. And then you know your cost of production, okay, your cost of production is C of x, okay, x is quantity because we don't know how much quantity is. Okay, let me do this a little bit different. So c of x, there you go. This is your cost function is 0.75x plus 10.75. Okay, that's your cost function. Now, if I assume your demand curve is linear, okay, and what your demand curve, like how, find your demand curve. Okay, well, so here, these two pieces of information tell you your demand curve, right? Because it's telling you when price is this, quantity is this, when price is this, quantity that. So there are 2 points you already know on your demand curve, and we know demand curve is linear, so it's a straight line. Then, okay, the question is, well, how do I find my function? Well, we have to go back to last chapter where we said, okay, how do you find your equation of a line when you know 2 points on that, right? So the general form we said is if the 2 points is x1, y1, and x2, whoops, let's see, y2, okay, then first of all, you can find the slope, right? We said the slope equals rise over run, which is y2 minus y1 divided by x2 minus x1, right? That's the slope. Then once you have the slope, then your functional form is y minus, okay, y1 equals the slope times x minus x1, or you can use x2, doesn't matter, okay, because you have point and slope for this. So this is a quick review of what we talked about last week. So let's apply that to this particular scenario. So we know that the slope in this case equals, okay, 41 minus 29. Wait, let me think. Nope, sorry. Okay, take back, because remember, y refers to the vertical axis here, and on your demand graph, vertical change is price change. So I'm glad I made that mistake, so I can show you how not to do it, right? So your vertical change is your new price minus your old prices, so it's 1.15 minus 1.45. That is your vertical change of rise, and then run is the quantity change, okay? So at 1.15, quantity is 41. At 1.45, quantity is 29. So that gives you a negative 0.3 divided by, okay, this is 12. And it's equals negative 0.025. Okay, that is the slope of your line. Once you have this, then you can say, okay, well, then my functional form, y is f of x, right? I know that. So it's f of x, then minus either one of the y value, which is in this case, let's say we use the first point, 1.45. That I know equals my slope, which is negative 0.025 times x minus your x value, in that case is 29, right? It came from this part right here, okay? Excuse me. Okay, now if you clean this up, okay, then this equals f of x, okay, equals negative 0.025 x plus, okay, negative 0.025 times 29 gives you 0.075. Then you move the 1.45 to the right-hand side and make it a positive number. And then that gives you f of x, okay, equals negative 0.025x plus 2.175. Okay, so that is how you figure out the functional form here. Okay, so wait, let me see. Did I do the math right? 1.25. Oh no, so hold on. I think I made a math error. I just copied my notes, but let me double check. So 29 times. Yeah, sorry. I wrote this number wrong. Okay, so 29 times 0.025 is 0.725. Okay, there we go. So that's how we get the 2.175. Okay, but this is your functional form for your demand curve. And if you don't want to use f of x, more traditional, not traditionally, but the custom we just used in the last question, you can change this to d of x. You can say demand is negative 0.025 plus 2.175, and that is my demand curve. Okay. Okay. All right. So once you have the demand curve, then you can say, okay, well, same thing. I can figure out, maybe for the next part, let's say, what is your revenue function, right? So your revenue is a function of x. X is the quantity, and that is how much you can sell times the price, right? So that is your d of x times x, right? Price times quantity, and that gives you negative 0.025x plus, there's a x squared, I should say, plus 2.175x. That is your revenue function. And then if I ask you the same question like I did with the last example, what is the profit function? Then you know that your profit function pi of x equals your revenue minus your cost. And cost function was given to us. Where it is. Yeah, right here. So you just do these two equations subtracted to each other, okay, where you have negative 0.025x squared plus 2.175x minus, okay, and the 0.75x plus 10.75, and then if you do the math, this will eventually equal negative 0.25x squared plus 1.425x minus 10.75. So, okay. Anyway, so this is how you kind of use the functional form and apply it to different situations, including your economic examples. Okay. All right. Again, I hope you practiced as we went along, and then if you had questions, definitely write them down, and we'll talk about them in class on Thursday. Okay. All right. Now, when it comes to functions, what you will solve most are just linear and quadratic functions. So linear functions are functions where the power of x is just 1. You don't have square terms or anything higher than that. And or you can, I guess x, the power can be 0. You can have f of x equals a constant. That's also a linear function. So linear functions is, the power of x no bigger than 1. And then quadratic function is when you have a second degree power on x. So x squared is in there somewhere. Okay. So that's a big difference. And now in a very general form, right? So you can say the linear function form is f of x equals, okay, mx plus b, right? Well, sorry, yeah, I should say x. Yeah, x can be just the power 1, because power 0 makes it 1, and it's a constant. But in that case, you would still have this form, but where in that case m can be 0, right? When m is 0, that's when you have a linear function that just equals a constant. But if m is not 0, okay, that is when you have what's called a first degree function, okay, where you actually have a function that's not just a constant, okay. Then your quadratic form of a function is when f of x equals ax squared plus bx plus c, again, where a, b, and c are real numbers, okay, and a doesn't equal 0, because if a equals 0, then that would give you your linear function, okay? So a cannot be 0 for it to be a quadratic function, okay? Now, when it comes to a quadratic function, okay, it's not linear anymore, then your graph is a parabola, and so it's kind of, well, it's a curve with an end on one side, and then opens up to another direction, right? So connected to this, okay, there's a 1 point on your graph that's called a vertex. Okay, the vertex is where your graph changes directions, okay, if you will. So this is the point where your graph changes directions, or just directions, okay. So if it was decreasing, that's the point where it starts increasing. If it was increasing, that's the point where it starts decreasing. We call that the vertex, okay? And it can give you either a maximum or a minimum for that function. And so that's one way to kind of find the maximum or minimum without learning calculus just yet, okay? And of course, a parabola is also a symmetric image, okay? So if you draw, let's say something like this, then there's going to be a line, okay, that can become the axis where you have a mirror image on each side of this line. And this line we call the axis of symmetry. Okay, and so when it comes to a quadratic form, and so the graph of something, let's say if you have a function, let's call it g of x equals, okay, a times x minus h squared plus k. If you can change your quadratic equation into some kind of form like this, okay, where a, h, and k are real numbers, okay, and again, a doesn't equal 0, so it's actually a quadratic equation. When this is the case, this is a parabola where the vertex is going to be the point of h and k. Okay, that is going to be where the graph changes directions. Okay, and compared to your similar function of fx equals x squared, which is the simplest quadratic equation. Okay, so the gx, the parabola, is narrower. Okay, so g of x parabola is narrower, okay, if the absolute value of a is greater than 1, okay? and it's broader. Okay, so g of x parabola is broader compared to f of x equals x squared. Okay, if the value of a absolute value of a is between 0 and 1. Okay, now it will look exactly the same with if a equals 1. Okay, so now related to this, okay, if a is greater than 0, okay, because it cannot be 0 itself, then this parabola opens upward. So it will look like this, okay? And of course, if a is negative, then the parabola will open downward, right? Okay, so these are just rules, general rules that you can apply to a particular, quadratic function, okay? So let's look at an example, okay, based on the rules we have. Let's say that we have a function, okay, so example, we have a function that's f(x) equals negative x squared minus 2x plus 3. And I want you to find the vertex, so where the graph changes direction, and the x-intercepts. Okay, now if we change this a little bit, right, then we can apply the rule we have above, right? So if we say this equals, okay, negative of x squared plus 2x minus 3, right? Everybody with me so far? Okay, and we want to change this into something that we can get into the format of a times x minus h squared, right? Because if we plus k, if we can get the function into this form, then the vertex would be very easy to identify. So a here is -1. We can see that, but how do we change it into this format right here? Well, let's manipulate this a little bit, right? Let's say this equals x squared plus 2x. Okay, if I want to do minus 3, then I can do plus 1 and then minus 4, right? Because plus 1 minus 4 is minus 3, right? But what this allows me to do is negative of x squared plus 2x plus 1, okay? Then negative makes it plus 4. And then this form right here, okay, becomes negative of x plus 1 squared, right? You can expand this out and verify with me, but I have changed into something I can make it into this form. So plus 4, don't forget to lose, not to lose that. So this is what I can change this functional form to. All of a sudden, I know that here a is -1, h is, well, remember, we have to do x minus h. So even though here is x plus 1, really it's important for you to know that this is x minus -1 squared, okay? Now let's put it this form. So h is -1 and k is 4. So once I have this form, I know the vertex is the point where it is, see, h and k, so it's -1 and 4, okay? And then if I were to find where my x-intercepts are, okay, that is when you set fx equals 0. So you have, in this case, negative x squared minus 2x plus 3 equals 0. And then just solve this with your quadratic equation, right, where x equals, okay, well, yeah, I guess one more step. So this is x squared plus 2x minus 3 equals 0, because we need the constant in front of x squared to be positive to apply the quadratic equation correctly, right? So x squared equals negative b, which is negative 2, plus or minus, okay, the square root of b squared, which is 4, minus 4 times a and c. So 4 times a is in here 1 now, right? That's what a is. And so 4 times 1 is 4, and then 4 times negative 3, which is c, is negative 12 divided by 2a, which is 2. Okay, so that gives you x1 equals, okay, negative 2 plus the square root of 16, which is 4, divided by 2, which gives you 1. Okay, then x2 equals negative 2 minus 4 divided by 2, and that gives you negative 3. Okay, so your then your x-intercepts, okay, are when x1 equals 1 and when x2 equals negative 3, then you can plug them back in and say, okay, my x-intercepts is 1 and 0, and, okay, so x-intercepts, I should say, okay, and negative 3 and 0, because we know for your x-intercepts, y has to be 0, so f of x has to equal 0. Okay, all right, I hope this helps. Now, to kind of show you what this graph looks like based on what we've talked about. So if you have your x here, y here, 0 here, then 1, 2, 3, negative 1, negative 2, negative 3, okay? And actually, that was not what I intended to do. Okay, so let's just fix this. I just wanted to make sure this point looks fairly even to the other side. There we go, negative 1, negative 2, negative 3. Then you have 1, 2, 3, and 4. Okay, so we know the vertex is at negative 1 and 4, so that means it is this point. That's your vertex right there. And then we know the x-intercepts is 1 and 0 right here, and negative 3 and 0 right there. So this graph looks something like this, okay? And specifically, I guess this should go like this. Okay, because if you do your y-intercepts, you'll see that 0 and 3 is your y-intercept, so you've got to make sure it goes through that point. But this is what this graph looks like. And then its axis of symmetry is y equals negative 1, which is this dotted line, right? So it should be a mirror image both sides of that dotted line vertically. Okay, so again, I hope this helps explain a few concepts we have just talked about and solidify it. Okay, now another kind of general form, if you want to look for a vertex of a quadratic equation, okay, if your quadratic equation's form is the very general ax squared plus bx plus c, then the vertex is always going to be, okay, negative b over 2a and f of negative b over 2a. And that then, if you solve the f of x, then that's negative b divided by 2a, and then 4ac minus b squared divided by 4a. Okay, so this is always the vertex of a quadratic equation taking on this very general form. So if you can put your quadratic equation into this general form, then you can find its vertex by applying this rule right here. All right. Okay, so quick example, right? So let's say f of x is x squared minus 4x plus 8. Tell you, okay, well, this is your quadratic equation. Where's your vertex? Where's the, in this case, minimum of your curve? Because here a is positive, so it's opening upward, right? And so in that case, I know the vertex is, okay, negative b, which is negative 4, divided by 2a, which is 2. And then here is 4 times a is 4 times c is 8 minus b squared, which is negative 4 squared, divided by 4 times a, which is 4. So that gives you, okay, negative 4 is positive 4 divided by 2 is 2, okay, then 4 times 8 is 32, minus negative 4 squared is 16, so it's 32 minus 16 is 16 in the numerator. 16 divided by 4 gives you 4. So 2 and 4 is the vertex of this particular quadratic equation. Okay? All right. Okay, so I hope that makes sense and helped you. And here in your practice, you probably saw a lot of graphs of different equations, and it's important to understand them, but I don't want you to focus on drawing the graph of a really weird equation somehow. That here the key is for you to understand the properties of the general quadratic and linear functions, and don't get caught up on drawing the weirdest equation, forms and etc. So anyway, and I just wanted you to keep that in mind. Okay, so let's look at another example really quick. Okay, so let's say you have an equation where it is g of x, oh, that's terrible, g of x, okay, equals x squared plus 6x plus 5. Okay, so the first I want you to find the vertex. Okay, so again, applying this particular, rule here, we know the vertex is negative 6 divided by 2, okay, and 4 times 5 minus 6 squared divided by 4, right? Because that's just applying this rule right here we have just learned about, and that gives you negative 3 and negative 4. Okay, hope everybody is with me. And now B says, let's say I want you to find the X-intercepts. Okay, and that again is when g of x equals 0, right? Because X-intercepts is when y value is 0 and y value is g of x, the function, right? So that is when you do x squared minus 6x plus 5 equals 0, and you want to solve this. And so that tells you x equals, okay, negative b, which is positive 6, plus or minus, okay, b squared, 36, minus 4 times a and c, which is 20, okay, divided by 2a, which is 2. So that gives you, okay, 6 plus or minus, okay, 16 square root, which is 4, divided by 2. So that gives you x1 equals 6 plus 4 divided by 2, which is 5. X2 is 6 minus 2 divided by 2, which is 1. So your let's see, did I miss anything here? Oh, whoops, sorry. Plus 6 here, so that changes everything. That changes it to, okay, yeah, -5 and -1 because, you know, or maybe I should be more careful and just say, okay, so -6 plus 4 is -2. -2 divided by 2 is -1. And -6 minus 4 is -10. -10 divided by 2 is -5. Right? So your x-intercepts is -1, 0, and -5, 0. Okay. Hope everybody is with me. I know you know, shows you that even when you're experienced, you always got to go back and check your work and make sure you didn't miss a plus sign or minus sign somewhere, which totally changes things. Okay. So now, so let's say, you know, third one is I want you to find 2 points on the graph of your parabola other than the vertex and the x-intercepts. Just tell me 2 points that you know exist. And so the easiest way to do that is to just, you know, plug 2 different values of x's in there and find out what g of x equals to, right? So let's say, you know, first you want to try x equals, see, -5 is already in the intercept, so you can't do -5. Let's say, well, how about we do -6, right? When x is -6, then g of -6 equals, okay, -6 squared plus 6 times -6 plus 5, and that gives you 36 minus 36 plus 5, which is +5. Okay, so then 1 point is -6 and +5. Okay, and another one, I asked for 2, so you can do, let's say maybe x is -2, and then g of -2 equals -2 squared plus 6 times -2 plus 5. And if you do that, that's 4 minus 12 plus 5, which gives you -3. So another point on your parabola is -2 and -3, right? So just, you know, sometimes it's good to verify these values by looking at them. And then finally, let's just draw a quick graph and see what your, let me drop this lower, see what your parabola looks like, right? So x, y, 0, and we know that the vertex for this is -3 and -4, so we want to have, you know, -1, -2, -3 right here. Then here you have -1, -2, -3, -4 here. So if you come down to there, to this point, this is your vertex. You know, this is where the graph changes its direction. And since here, the original form tells you, okay, x squared here, so a equals 1, right? Because usually we have ax squared plus bx plus c. So a equals +1 right here. That tells you your parabola is going to be upward opening. So opening upward, okay? Then your x-intercepts we found to be -1 and 0 right here, okay? And the other one is -5 and 0. So okay, then that means, well, wait, let's see. Did that, yeah, is that right? Okay, what is your vertex? Yeah, -3, -4. Oh, whoops, I got these two. See, you can never be too careful. I got these two totally reversed. Okay, so it's -3, -4. So that means it's -3 here and -4 here, because the first number is on your horizontal axis. The second number is on your vertical axis. Okay, there we go. Now that looks better. Okay, so you know it looks something like, can't be a straight line. So it looks something like this. And over here it looks something like this. Okay, that's what your parabola looks like for this particular graph. Okay. All right, so again, hopefully that makes sense. And hopefully as we go along, you can see that even I make mistakes. So make sure you be careful, okay? And fortunately, I've caught my mistakes so far. And if you see something I did make a mistake and forgot to catch it, please make a note and tell me in class. Then I will definitely correct it and talk about it, okay? All right, so another example, okay, using the vertex idea. So let's say that you don't know derivatives yet, but I tell you that, well, let's say your cousin owns a Airbnb rental place in Florida, okay? And she has figured out her revenue takes on this form where A equals 300x minus 0.5x squared. And she's asking you, hey, X here is, let's say, how many days she can rent out her Airbnb each year. And she comes to you and say, hey, how do I maximize my revenue, right? So how do I maximize my revenue? Okay, now again, with derivatives would be very, would be very easy and quick to figure this out, but you don't have derivatives yet. Okay, so by looking at this, I hope you realize, well, first of all, A here, right, this really is negative 0.5 x squared plus 300 x should be in this order, right? And A here is negative 0.5. It's a negative number, so you know your parabola looks downward opening like this. So that means your graph horizontally is the number of the X is the number of days you can rent out your cousin's Airbnb, and then I don't know where the vertical axis should lie, but let's say that it looks something like this. No, it can't be like that. Okay, it looks something like this because you can't have negative days that you rent out. So this is your R of X, right? This is your revenue. So clearly, okay, your maximum revenue is right here at the vertex, right? That's the highest revenue you can get given your revenue function. So your job is to then find out what this value is for your perfect X, call this X star, right? How many days should your cousin rent out her Airbnb in order to maximize her revenue? Okay, so let's find the vertex, right? Given your equation from before, okay, and we know that, well, the vertex for your quadratic equation, okay, is negative b over 2a and then 4ac minus b squared divided by 4a, right? So we already knew that. So let's just apply that. Negative b, which is 300 divided by 2a. 2 times a negative 0.5, a is negative 0.5, so that's just positive 1. And no, sorry, not positive, negative 1, because 2a is 2 times negative 0.5, which just gives you negative 1, okay? And then up here, 4 times a times c, c here is 0, right? So that's 0, then you have negative b squared, which is 300 squared, which is 90,000, okay? Divided by 4a, again, that is negative 2. So that then becomes 345,000. Okay, so this tells you, okay, the ideal days you should rent out is 300 days a year. okay? And okay, your revenue when you rent out $300,000 a year, your revenue is going to be $45,000. Okay, that's what your cousin's Airbnb, particular problem would be, right? So that's the vertex, which is the highest revenue your cousin can get, and then maybe because she rents out too much, then there's going to be a negative effect on the price she can charge or something. The point is, okay, you can, if her revenue function takes on this form, then you can tell her even without knowing calculus how many days she should rent out. Okay. All right. I hope that makes sense. I need a quick little break, so I will be right back. All right, guys, I'm back, and let's continue. Okay. So in this chapter, there are also some other common forms of functions that your exercise talks about, and hopefully you learn about it. I'm not too concerned about those. I'll just mention the common forms, and then tell you what you're supposed to know, but it's not of essential importance for this chapter, right? So some other common forms is when you have f of x equals a times x to the nth power, okay, or f of x equals a divided by x to the nth power, okay, or where you have f of x equals a times like the absolute value of x. Okay, so the focus here in your book or website is the graphs of these particular functions, forms, and you can look at them, but again, I'm not expecting you to be able to draw by hand these particular functional forms. So as long as you know what they roughly look like, and you can identify, if I give you, let's say 4/3 to, times x to the 4th, and then give you a bunch of different graphs, you should know that x to the even power will always be some kind of a function that the axis of symmetry is going to be the y-axis, right? So it's always going to be something, like this, if you will, right? Whoops, that's a terrible, it's not symmetric at all. Okay, it'll be something like this, or actually in this case, probably something like this, but just the important thing here is to be able to recognize these graphs, what roughly they look like. You should know that x squared, x to the 4th will never look something like, let's say, like this, right? Well, pretend it went through the origin, right? It'll never look something like this, because this can never have any negative value like down here, right? So if I give you an option like this, you should know this is wrong, okay? That's what my expectations are, okay? So be familiar, you can read about it, but then again, I don't expect you to be able to draw anything from this particularly, okay? So now the next thing I want to focus a little bit on, again, not super heavily, is transformations of functions, okay? So let's say that if you have f of x as a function, then and where g of x equals f of x minus h, okay? So if this is a case, you know that g of x, okay, will have the same shape of f of an x, f of x, okay, but shifted by this by the distance of h. Okay, but shifted. Okay, let's say right by h if h is greater than 0, or it'll be shifted left by h units if h is less than 0. Okay, so when you have gx and fx with this relationship, gx is the same thing, just shifted horizontally left or right. Okay, now similarly, okay, if you have fx as a function, but gx equals f of x, okay, let's say plus k, this is gx having exactly the same shape, but then shifted, okay, upward if k is greater than 0, and downward if k is less than 0, right? So this is the whole f of x already finished, and then plus k, so that's when you shift it up or down while having hold on to the same value, okay? Now, in this first case, the form of x minus h is crucial because that's how you figure out which way your graph is shifted. So if you have, okay, x plus 5, for example, it's essential for you to write it as x minus -5 in order to remember what h is and which way this is shifted, right? So in this particular case, and then h is less than 0, so you know gx is shifted to the left, okay? At least for me, this is left, and by the size of 5, right? So always keep it in this x minus h format, okay? Even if it's a positive number that you're seeing there, okay? All right, and then okay, let's see, what else? Okay, and another common thing you see is reflecting with respect to the axes. Okay, what I mean is, well, if you have a function of f of x, whatever the function is, and then you have something of gx equals negative of f of x, okay, then this is the reflection of the graph of f with respect to the x-axis. Okay, so then g is the reflection of the graph of the function f, okay, with respect to, WRT is with respect to the x-axis, okay? So what that means is you take whatever f is, if f is like this, you flip it over, and then it becomes something, well, I can't do this with my hand very well. Never mind, forget it. I'll just draw it on here, okay? So if f of x, let's say, is this. If this is f of x, g of x would be this. That's better. Should have just used my iPad. Okay, so now if we have g of x actually equals f of negative x. Okay, so instead of saying you just negate the whole function, instead you plug in negative x to the function of f. Then in that case, that is when g is a reflection of f with respect to, so I'll just do dot, 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 dot with respect to the y-axis. Okay, so that is when you have, let's say, if f of x is something like, you know, this, then g, so this is f of x, then g of x would look something like this. Okay, so you just flip it around the y-axis. Okay. Now, so the difference is, you know, when you negate the entire function, like we said, then you're flipping it around the x axis. If you're plugging in the negative x value into the function of f, then that's when you're negating it horizontally, right? Flipping the mirror image. Okay. All right. Okay, now let's talk about stretching. Okay, so again, we start with f of x being a function. Okay, now if you have g of x equals a times f of x, okay, so that means your function g, okay, so g is f, okay, stretched vertically, okay, if a is greater than, whoops, not 0, greater than 1. Okay, so it's similar shape, but pulled bigger vertically. Okay, but if a is less than 1, then g is, you know, the graph of f. I'm just writing f, but it's really the graph of f. Okay, compressed vertically if a is between 0 and 1. Okay, so if it's a factor that's smaller than 1, then f is taken, you know, and compressed vertically, looking very similar in shape, but a little bit different. Okay. All right. Now, okay. All right. So we can also look at the y-axis symmetry. Okay. So the graph of a function f has y-axis symmetry, or you say is symmetric with respect to the y-axis if f of a negative x equals a negative of fx. Okay, so in that case, then this is a graph that looks symmetric around the y-axis. Okay, if this is the case. Okay, so we call this, you know, y-axis symmetry. Okay, now we can also have origin symmetry. Okay, so if you have a function of f negative x equals negative of f of x, whoops, oh, you know what, sorry, I wrote the wrong thing. So with the first one, okay, with your y-axis symmetry is f of x negative x equals f of x. Sorry, I jumped the gun a little bit. Okay, so that is when you have y-axis symmetry. So whether it's -1 or +1, it gives you the same y value, right? So that would be your y-axis symmetry. If your f of a negative x equals negative of f of x, then you have what's called the origin symmetry. Okay, so origin symmetry then would be something like this. Let's say x and y. So let's say something like this. Okay, so you know, my 1 gives me +1, and then -1 would give me, okay, -1, right? So you are symmetric with respect to the origin. So this is, okay, your origin, okay, symmetry. Okay, so again, these are good rules to know, and I do want you to be able to figure it out, but I'm not expecting you to be able to draw sophisticated graphs on your own without any help of a calculator or computer program. But I do expect you to be able to recognize which graph represents the function I give you, right? If I give you a function where f of negative x equals negative of fx, like the second scenario here, then given different graphs, you should be able to identify this one to be the most likely candidate for that function, right? All right. Okay, so also, okay, if you have a case where, okay, you have a function of fx, okay, so let's say you say f of the function f is increasing, okay, if x1 is less than not equal to, less than x2, and also, okay, f of x1 is less than f of x2, okay? So then at least on a particular interval, okay, where x1 and x2 are, then we call this an increasing function. Similarly, okay, you say fx is decreasing, okay, if x1 is less than x2, but then f of x1 is actually greater than f of x2, right? And then finally, okay, this is constant if x1 is less than x2, but f of x1 equals f of x2, right? So on the interval, this doesn't mean this is true for the entire function necessarily, but on the interval where x1 and x2 are, right, this is how you can determine what the function looks like, okay? All right, now, so we can look at some examples really quick, okay? So let's say you have a function where it says v of x equals x squared over 3 minus 2, okay? And I'm asking you, okay, well, determine the more basic function that has been shifted, reflected, stretched, or compressed by v of x. Well, then hopefully the most basic function that v of x took and then kind of manipulated would be f of x, okay, so point A equals x squared. This is the base of Vx changing things, right? Now the question is, well, what did Vx do to the poor f of x equals x squared to make it look all weird, okay? Now let's see, first of all, is there any horizontal shift? Okay, the answer is, well, no, okay? Otherwise, it would be x minus something squared. Here, it is still just x squared by itself, no shift horizontally, okay? Now, what about vertical shift? Well, the answer is yes, and it's shifted downward by 2, right? Because it's minus 2, okay? Now, what about stretch or compress or compression, right? Okay, stretch or compress. Well, the answer is yes, right? Because you have 1/3 times x squared in the functional form of Vx. So that means, okay, you took f of x and compressed it by 1/3. Okay, and then finally, is there any x-axis reflection or y-axis reflection The answer is no, right? So this is the kind of analysis I expect you to be able to perform. So I'll give you a functional form that doesn't look very clean, and you tell me, what is the base function that this came from, and how has this function kind of changed the poor basic function form? Where did it shift it vertically, horizontally? Sometimes you have both, right? If this had been v of x equals, x minus 3 squared divided by 3 minus 2, then this would have shifted both horizontally and vertically, right? But this kind of is the kind of question that I want you to be able to answer from this part of the chapter, okay? All right, okay, now my iPad is quickly draining its power, so hopefully we can finish this video. Okay, the next part of the chapter is all on polynomial functions, right? Polynomial functions is just a function with many different parts of a function, if you will. Okay, and so there are some concepts, and your book talks about where, let's say, if you have a polynomial equation with, n degrees, and what we mean by that is you have a n times x to the nth power plus a n minus 1 times x to the n minus 1 power plus dot 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 plus a1 x raised to the first power plus just a naught. And because at the end, this is really x raised to the 0 power, which is 1. So a naught or a0 times 1 is just a naught itself. Okay. If this is the case, okay, where n is a non-negative integer, so n is non-negative. Oops, sorry. Okay, and then an minus 1, dot, 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 all the way to a1 and a naught are constants. So these are numbers. Okay, and now we're, okay, an is not 0. Then we call this particular function, this equation has a degree n. So this is a polynomial equation of n degrees with, okay, a n as what we call the leading coefficient. Okay, so that's kind of the name you have here. Okay, and now when it comes to a polynomial, okay, what you're trying to look at, there's I don't know if your website gives you this nice table or not, but if we look at the possibilities, okay, where you say an is positive versus an is negative. Okay, so depends on what is the coefficient for the first term, the biggest, highest power term of x in your equation is, and then where n is even. So you have an even number of, your polynomial function versus n is odd. Okay, because the nth power, the highest power, whether it's even or odd. Okay, and then we say, you know, as x approaches negative infinity, okay, your function, let's call it p of x, because it's polynomial function, will approach positive infinity, okay? And as x approaches positive infinity, then p of x in this case would approach negative infinity, okay? And so what this looks like on a quick little graph is something like this, okay? That's your equation, so x and y, okay? Now, versus n is odd when an is positive, so the first coefficient is positive, but the highest power of your x is an odd number, okay? Then as x approaches negative infinity, your polynomial function p of x will also approach negative infinity. And as x approaches positive infinity, p of x will approach positive infinity. Okay, so what that looks like is that the graph will fall to the left and rise to the right. Okay, so it can be something like this. Okay, so this is a possible, equation form for a positive leading coefficient and an odd number of highest power for your x term. Okay, and then over here, okay, when an is negative, the leading coefficient is negative. So that means as x approaches negative infinity, p of x is going to also approach negative infinity, and as x approaches positive infinity, p of x also approaches positive infinity. But because this is an even n, the power on your highest, the highest power on your x term is positive, so it's going to be symmetric around your y-axis. So it'll be something like this, okay? And then when n is odd, the highest power on your x term is odd. So as x approaches negative infinity, okay, p of x in this case would approach positive infinity. As x approaches positive infinity, p of x approaches negative infinity. And then since it's odd, it's no longer symmetric around your y-axis. And so what happens is then the graph will rise to the left and fall to the right. So you'll have something, in this shape. Okay, so that's the general shapes of your polynomial functions, depending on what your leading coefficient is, whether it's positive or negative, versus your highest power on your x is. Okay, so again, that is kind of the core idea I want you to be able to get out of this. And if you can remember this, then you can probably identify a bunch of graphs that will be thrown your way fairly well. Okay. All right. Then, okay, finally, let's talk about rational functions. Okay. So let me see if my charger can reach my iPad so I don't have to run out of power. What? All right, we're back in business. Okay. Nope. Okay. All right, So last topic for chapter 3. I know this has been a long chapter, probably long video, and hope you took some breaks. It's rational functions. Okay, so a rational function is a function that can be written as f of x equals, okay, p of x divided by q of x. So really it's just two functions divided by each other. This is called a rational function, okay? Oh, I already said no. Okay, where p of x, q of x are polynomials, okay, polynomial functions. Of course, q of x cannot be 0, right? Because otherwise it would be undefined. And so that means the domain for f of x then excludes all the real numbers that would make q of x equal 0, because that would make the whole f of x undefined, right? Okay. Now, a function like this, a rational function, then usually has asymptotes. So asymptotes are lines that this function will forever get close to, but never really reach or never cross. Okay, so it can be a vertical asymptote. So let's say if you have a function that actually forever gets close to y, right? So maybe it goes like this. It goes really, 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 really close to y, but it never reaches y or touches y. Okay, and to determine, okay, what the I guess I'm jumping the gun. We'll talk about how to determine the vertical asymptotes and versus horizontal. Okay, and then sometimes the rational function will have horizontal asymptotes. That means you forever approach a horizontal line, but then never actually cross it and get to it, right? So if that's the case, it can be something that like looks like this, right? Where you get, whoops, no touching. Okay, where you get forever close, but don't ever touch the x-axis in this particular graph, right? So, and then if, of course, you don't approach either a vertical or horizontal asymptote, you don't just approach either horizontally or vertically to a line, then you have oblique asymptotes, where that's a line that's that you still get closer and closer and closer to, but it's just not horizontal or vertical. Okay. Now, the notation for asymptotes, okay, and is something like this. Okay, so when you have x approaches c with a little minus sign, that is describing the behavior of a graph as x approaches the value of c from the left, the negative side. Okay, or if you have x approaches c with a positive sign, that describes the behavior of your graph as x approaches c from the right, which is the positive side. Or if you have x just approaches c, then that would be saying the graph, describing what the graph is doing when x is coming on both sides toward a particular c. C is just a particular, asymptote or value that your x can take on. Okay. Now, for your vertical asymptote, okay, and so vertical asymptote. Okay, so if you have a rational function that's f of x equals p of x divided by q of x, okay, and this has been written in the reduced form, which means p and q no longer have any common factors. Okay, if they do have common factors, you want to eliminate those first. You want to, cancel them out. And then, so if this f of x is already in the reduced form, okay, then the vertical line, so the vertical line of x equals c is a vertical asymptote. Okay, if and only if, okay, c is a 0. Oops. Sorry. Okay, c is a 0, okay, of the polynomial q. What I mean by that is you set q of x equals 0 and you get x equals c. So if that's the case, okay, so when you set the denominator to 0 and whatever you solve x to be, then this line of x equals c is a vertical asymptote for the function of f of x right here. Okay, now I'll give you some examples, right? So for example, if let's say we have h of x equals, okay, 32 divided by x plus 2. So the question is, does this function, this rational function of h of x, have a vertical asymptote? The answer is yes, because if you set x plus 2 equals 0, that gives you x equals -2. Then that means h of x will forever approach, okay, x equals -2, but never get there. So x and y, so x equals -2 is this straight line, right? So this straight line is a asymptote for h of x, okay? So that's how you determine whether a vertical asymptote exists for a rational function, okay? All right, now what about horizontal or oblique asymptotes? Okay, well, let's look at that. Okay, this one is a little bit more complicated. Horizontal and oblique asymptotes. Okay, so this one, again, if we say if the function of f of x is p of x divided by q of x, so two polynomial equations divided by each other, okay, and let this be a rational function, okay, so that means p, let's say, is an nth degree, okay, polynomial with a leading coefficient okay, a of n, right? So we talked about this just a few minutes ago, okay? And then let's say q is an mth degree polynomial with leading coefficient b of m, okay? And then there's no common factors in p, x, and qx anymore, so f of x is the reduced form, okay? If this is the case, okay, then the asymptotes for x are found as follows, okay? So one is if n is less than m. So that means the highest power in your numerator for x is less than the highest power in the denominator for x. If this is the case, okay, then y equals 0, your horizontal, your horizontal axis or your x-axis, right? This is the x-axis, okay, is the horizontal asymptote for f, okay, or of f, if you will, okay? So that's the first scenario. Second is, well, if n equals m, so the highest power of x is the same in your numerator and your denominator, okay? Then the horizontal line of y equals a of n divided by b of m, the leading coefficient, then is the horizontal, okay, asymptote of f. So this becomes the line that f of x will always get close to but never reach, okay? Then the third scenario is that if n equals m plus 1, okay? So n is greater than m by 1 degree. Then in that case, okay, the line y equals gx, okay, is an oblique, okay, asymptote of f, or for f, if you will. Okay, it should be for f, I guess, where, okay, g is the quotient polynomial obtained, right? So quotient polynomial of, okay, p divided by q. Okay, that's when you just divide those two functions and get the functional form of g, and then that particular function becomes the line, because, you know, since n is m plus 1, when you divide the two, then gx is going to be x with just the first power, so it's a straight line, and whatever that line is becomes the asymptote, the oblique asymptote for f, because f will forever get to that line but never cross, okay? So if, let's say, f of x is whatever x cubed divided by whatever x squared, then when you divide the two, you're going to end up with just x, right? So raised to the first power, and that's a straight line. And then that line you get from p divided by q is the asymptote for f of x, okay? Then finally, okay, if n is greater than n plus 1, so it's more than 1 power higher in the numerator of f of x than the denominator, okay, then there is no straight line, okay, horizontal or vertical. Okay, or I'm not, sorry, not horizontal or vertical, horizontal or oblique, that's what I meant to say, okay, horizontal or oblique, okay, asymptote for f, okay, because if n is more than 1 power higher than m, so that would be the case where x to the 4th power in the numerator divided by x or x squared in the denominator. Once you do that, you still end up with an x squared, which cannot be a straight line. So there's no straight line that can be something that f of x is approaching to but never reach, okay? Again, I hope this makes sense. And it's kind of a lot of interesting, weird little rules, right? So let's do a couple practice really quick and then see if that makes sense. Okay, so let's see, look at my notes. All right. Okay, so let's say we have, okay, f of x equals negative 3x plus 1, okay, over x plus 4. And my question is there any vertical asymptote? Okay, well, again, to find the vertical one is easy. You just set the denominator to 0 and solve for it, right? That tells you x equals negative 4 is your vertical asymptote. So yes, there is one, and this is how you get to it, okay? But let's look at some horizontal ones or other types. Let me see if I can find a good one. Okay, yeah, so let's say that you have f of x equals, okay, negative 9 divided by x plus 3. Okay, now first question is if there's any vertical asymptote. Okay, the answer is yes, x equals minus 3 or negative 3. Okay, now the next question is there one for the horizontal? Okay, well, here you can see in the numerator, the power for x really is n equals 0, right? And there's no x, so the power of x is 0. And then in the denominator, m, the power is 1 because you have an x. X is x raised to the first power. So if we go up to the rule here, it says, okay, n is smaller than m. This is the case where then we know, okay, you don't have to draw the graph, but y equals 0 or the x-axis is your horizontal, okay, asymptote. Okay, and then, if you look at other examples, okay, just follow the rule here. I'm trying to see, I don't think I have anything that's too much more complicated. Again, the goal here is not somehow we're going to use these polynomial functions or rational functions directly in economics, and I expect you to be able to draw a very complicated function in the graphical form by hand. But rather, okay, it is important to be able to recognize how to identify if there is an asymptote for a rational function, and if so, okay, what it is. So if you remember these 4 rules right here listed, okay, 1, 2, 3, and 4, then you can find that fairly quickly, because in economics we will have functions that approach an asymptote but never get there, right? So but anyway, but the key is I'm not going to give you a sophisticated function that asks you to draw it, but rather, okay, help me identify what is the most likely graph for a specific function, or if I say here's this graph for this function, which one of these is a most likely asymptote. And you need to be able to take these rules and then look at that function and say, oh, you know what, if it's number 2 or number 3 or number 4, okay, and then between A, B, C, and D, here is one that's the most likely graph for the asymptote with the rational function. Okay, so that's kind of the key form that I want you to understand. And anyway, that is all for this chapter. I hope you don't feel too overwhelmed, and I will see you in class. Come prepared with questions, okay?